For the final part of this project, we were tasked with working with a student at a university in Mexico to solve a turbine problem. The problem is a turbine takes 5,000 kilograms of water vapor at a pressure of 4,000 kilopascals at 300 degrees Celsius. This vapor enters into the turbine at a speed of 60 meters per second and is later discharged at 200 meters per second at a position 3 meters below the entrance. The turbine generates 570 kilowatts of power, and heat losses are estimated at 135 kilojoules per minute. A small portion of the vapor discharged by the turbine passes through the valve, which releases the vapor to the atmosphere. What is the temperature of the vapor at the discharge valve? Calculate the quality of the vapor at the discharge valve if it is humid. With this information, is it possible to determine the thermodynamic state of the vapor at the discharge of the turbine?
So the first thing we have to do in order to solve this problem is to draw a diagram of the system. Currently, the system we're dealing with is open because of the entry and exit of the water that happens. The diagram should look something like this. As we're dealing with it, the velocity of the water vapor coming in is 60 meters per second, and the pressure is 4,000 kilopascals. The valve, which is at the same level as the entrance of the water vapor to the turbine, is at atmospheric pressure, and the discharge at a distance of 3 meters below the entrance of the water vapor happens at a speed of 200 meters per second, where there's a power supplied to it of 570 kilowatts, and there are negative 135 kilojoules of heat lost. The negative is there to emphasize the loss of the heat, as stated in the problem. The easiest way to solve a problem like this one is to set up a table which looks as follows, where you outline the points at which you're observing, where our first point will be the entrance of the water vapor, our second one will be the discharge, and our third one will be where we're looking at the valve. At each of these points, we're interested in knowing the pressure, the temperature, and the enthalpy, as well as finally the thermodynamic state. We already know the pressure that occurs at some of these points. Initially, we have 4,000 kilopascals, and at the valve, or point 3, we have atmospheric pressure, which is 1 atmosphere, or 101.325 kilopascals. We also know the temperature that happens at point 1, which is given in the problem, to be 300 degrees Celsius. And for now, that is all the information we have about the problem, other than it is water vapor, so we know that it is superheated water, which is a thermodynamic state. From this, we go to a table of superheated water property values. We look for the pressure, which matches the one of our problem, and for the temperature, which matches the one of our problem. And we look down the enthalpy column to find the enthalpy that occurs under these conditions. In this case, that enthalpy is 2,961.7 kilojoules per kilogram. Once we have this, we can start looking at our thermodynamic equations at these 3 different points. The first point we're going to be looking at is point 3. Oh, it's a bit big. Make it a little thinner. Is point 3. We're going to be using the equation here for work. This equation involves the heat of the system, the work done on or by the system, the change of enthalpy, change of kinetic energy, and change of potential energy. But for all of these, we're only going to be looking at what happens at point 3. Since we know from our diagram and from the problem that our valve happens at the same level as the entrance of the water vapor into the turbine, we know that our potential energy is 0. And we know that our kinetic energy is 0 because we are assuming that the valve is closed and there's nothing going through it. Same goes for work, and there is no heat being lost or generated at the valve. This leaves us with a change of enthalpy at the valve equaling 0, which translates to, because of the way the system works, you have a change between, we're looking at the discharge, at the enthalpy of the discharge, and the enthalpy at the valve. Granted, the drawing is a little confusing, but the discharge occurs right before the valve happens. So, therefore, this change of enthalpy will translate into H at point 3 minus H at point 2 equals 0, which then means that H2 and H3 are the same. As a consequence of this, we have to look at the exact same equation at point 2. Here at point 2, we have a lot more information about what is going on. At point 2, we are given that we have a loss of 135 kilojoules per minute, and we have a power of 570 kilowatts, which translates to 570 kilojoules per second. We don't know the change of enthalpy, but we do know that since the water vapor is moving at this point, that there is a kinetic energy. This kinetic energy is the change of the velocities from point 1 to point 2 squared over 2. We also know, because the discharge happens at a height of 3 meters below the entry, that there is a potential energy, which is 9.81 for the gravitational, for the acceleration of gravity, and then the change of height, which when we're looking at it, our initial height is 0 as per our diagram, and our final height is at -3. We're then going to solve for these two parts of the equation, the kinetic and the potential energy. So we know, based off of the equation, that the units for kinetic energy, when that math is all worked out, comes out to be 9,800 meters squared per second squared, because this right here is half v squared, where the initial units of velocity are meters per second, all getting squared. A good thing for us is that it works out the exact same way with the potential energy, which gives us a value of 29.43 meters squared per second squared, for a total of 9,770.57 meters squared per second squared. Since these are not units that we're comfortable working in or know what they mean at all, we will be using a conversion factor. That conversion factor is 977.57 meters squared per second squared over 1 GC. And the GC works out to be, the GC is 1 kilogram meter over newtons per second squared. So when we actually perform this conversion, hold on. Over 1 GC. So when we finally perform this conversion, we're left with 9,770.57 Newton meters per kilogram, which coincidentally is 9,770.57 joules per kilogram. Once we have this, we can use the 5,000 kilograms per hour water vapor that the turbine takes in to convert this into units and values that we are more comfortable with. So this 5,000 is in kilograms per hour, which results in a total of 48,853 kilojoules per hour. And these units are compatible with enthalpy units. There's one more conversion that we're going to have to do after that. Once we know that the initial 9,770.52 meters squared per second squared is equivalent to this number, we know we can move on with the problem and tackle the other side of that equation. In order to get these into enthalpy-friendly units, we need to perform a few conversions. So, first, what I'm going to do is rearrange this whole equation in a way that's easier to understand. So, delta H equals negative 135 kilojoules per minute minus 570 kilojoules per second minus 48,853 kilojoules per hour. So we need these in kilojoules per kilogram. In order to do this, we convert through using the amount of water vapor, the kilograms of water vapor per hour that the system takes, along with a simple time conversion. And it looks as follows. Where this last one is in kilojoules per hour, as mentioned earlier. So, Walking you through this, it's obvious to see that minutes cancel with minutes, hours cancel with hours, which leaves us with kilojoules per kilogram. Here, seconds cancel with seconds, hours with hours, kilojoules per kilograms. And here, it's a lot simpler. Hours cancel with hours, and you're left with kilojoules per kilograms. After all these conversions are done, you're left with a change of enthalpy of minus 421.79 kilojoules per kilogram. Knowing that this is at point 2, we know that this change of enthalpy is actually the enthalpy at point 2 minus the enthalpy at point 1, which is equal to negative 421.79 kilojoules per kilogram. This allows us to solve for the enthalpy at point 2 because, I made a mistake here. That should be the enthalpy at point 1. So this allows us to solve for the enthalpy at point 2 because, as previously determined from our neat little table, we already know the enthalpy at point 1. So we add that to the change of enthalpy value that we got in order to determine the enthalpy at point 2. Which leaves us with an enthalpy at point 2 of 2,539.91 kilojoules per kilogram. Once we have this, we can go back to our table and fill in the enthalpy value at point 2, which is 2,539.91. Oh, I forgot a 9. Because of our work that we did at point 3, we also know that the enthalpy at point 2 and the enthalpy at point 3 are the exact same, which allows us to fill out this spot in our table right here as well. And once we know that,